Having fixed my Fnirsi IPS3608 in the last video by replacing the MOSFETs and a ceramic capacitor, I would now like to address what I believe to be another fundamental issue of this unit, and that is the fact that it overheats so easily. When using this power supply at maximum voltage and maximum current, it can just about handle that. But if you reduce the voltage down to something like 18 volts and then still have around 8 amps, so which equals about 145 watts, this power supply overheats within around 3 minutes or under. So in this video I would like to address that and see if I can actually get this thing to operate at that parameter without overheating. If you'd like to see some modifications to this power supply in an attempt to stop it from overheating, and a description as to why increasing the actual over temperature setting is a bad idea on this power supply, then this is the video for you. So let's go. So we'll start by having a quick look at the data sheet as regard to the MOSFETs used in the for the output stage of this power supply. And as we've already seen in the previous video where I replaced these guys, the MOSFETs are NCE P039N10M. Now these do have an extremely low RDS on of just 3.65 microohms. That's a typical value with a gate drive voltage of 10 volts. Now this arrangement we saw has two MOSFETs which are arranged in a high and low configuration, high side low side configuration. So without going into too many details, and I mean I'm not the guy to really tell you how to design a switching power supply using MOSFETs, but I do know some basics, and what that is going to tell us is that the MOSFETs themselves are going to change characteristics depending on the temperature of the case. Now, very simply speaking and very basic terms, we can actually see in the data sheet here that there is actually a derating factor for temperature. So that is 1.47 watts per degree centigrade. Okay, now that is represented in a graph which will be this one here. Just zoom in on that one a little bit. Okay, so this is the power derating graph. So this graph should represent the figure that we saw in the data sheet earlier. Now if we can just have a quick look at this graph for a moment. So you can see that the device is rated at 220 watts maximum, and that is from 0 to 25 degrees centigrade, and then from that point onwards then the temperature derating will follow this line on this graph. So we can see here that the standard setting for the over temperature limit is set to 60 degrees centigrade, which it's not easy to get an accurate measurement of that on this particular graph, but I'm going to assume that is less than halfway between the 200 and the 150 mark. So I'm going to say that that's like a third of the way between 150 and 200. So let's just say that that's 165, okay, just as for example. So at 60 degrees centigrade, then you have to derate each device to 165 watts. Okay, now the device itself is rated at 295 watts, which is the 36 volts times the 8.2 amps maximum output. So at maximum current, you can assume that very roughly speaking that each one of those two MOSFETs will be handling approximately 50% of the power. So therefore we have we've got about a 30 watt overhead, so we're going from 295 to 300, and so if we said it's 165 watts per device, that's 330 watts. So we've got a 35 watt overhead. Nothing is perfect, so the devices themselves actually have or consume power and have losses. The losses inside the device are very difficult to calculate, especially when you don't have the specific data that required to be able to do that. But there are things like the conduction loss, so that would be, you know, the loss within inside the component depending on the value of the RDS on. Now obviously that value, according to this data sheet, is quite consistent across the range. We've looked at that already. Let's just go back to that very quickly. So this is the RDS on across the current range, and yeah, they're basically saying it's quite consistent all the way up to 120 amps. But in addition to that, you do actually have the normalized graph. So this is not actually in ohms, this scale. This is the a factor, if you like. So at 25 degrees, your factor, multiplication factor, is 1, and then from that point onwards, so if we say we take 60 degrees, so they're basically saying that the normalized on resistance will be about 1.2 times whatever it is at 25 degrees at 60 degrees, for example. Okay, so when you're calculating the conduction loss, you have to take that into account. You've also got things like switching losses and the reverse recovery loss, and you know, the output capacitance loss, and there's a few others. So in total, when you add all of those things together, the MOSFET itself has internal losses. I think most of those are probably down to the RDS on. So in this particular device, in theory, that should be quite low. But even so if we take worst case scenario, okay, and you went into the settings and increased the over temperature setting to say 75 degrees, so at that point you're now under the 150 watts, and I have seen people saying that they've turned this value up to 90 or 100 degrees. Well, at that point you're really down, you know, you're down to nearly 100 watts of maximum power dissipation, so you're going to damage the MOSFETs by doing that quite badly. So that is the basic summary as to why they've set the over temperature setting to 60 degrees centigrade in the settings. They've made it adjustable, don't really know why, but anyway, to adjust that is quite dangerous unless you know you're going to operate this thing at much lower power levels. Increasing this temperature is, you're going to risk damaging the MOSFETs. What I intend to do is to try and get this thing running so I can keep the over temperature setting to 60 degrees, and I can basically put out maximum output current at approximately half output voltage, which is the test that I've been doing and has caused this thing to overheat very rapidly. Okay, so I'm going to start by just taking the front panel off again. Now, one of the issues that I did notice, and it's actually going to be really difficult to get that on camera, I'll try, so I need to angle that towards you guys. So if we can actually see inside there, you can see that there's a step here, which is where the side vent is internal in the unit. And what I actually noticed, if you look in the back end, was this heatsink actually goes right up against that the inside of that side vent. So any potential heatsink, unfortunately, is going to have to get narrower at some point to go around that, and that's my biggest concern at the moment. But anyway, so I'm going to start by removing the front panel. I think I've still got these marked from last time. Yes, I have. Let's get a screwdriver. Are they actually plugs? No. Okay, so we can get rid of that part for the moment. And I will just zoom the camera in a little bit so we can see a bit better what's going on. Okay, so the first thing I actually need to do is to separate the front panel from the screen itself. Now, I have done this once already in the previous video, so we need to undo that. There's several screws around here. Let's just get a better screwdriver. Maybe that one. No, maybe not that one. Maybe that one. Yes. So let's just remove all of these screws. 1, 8, 9, I believe. And that's in there. Got to take the knob off, I believe. Yes. Okay. So we'll put that to one side. So this is the heatsink itself. So we can see that the heatsink is actually secured with 2 pins onto the PCB. So what I actually want to do is to replace this heatsink, which isn't going to be overly easy. The first thing I want to do, I want to try and keep this one original. I don't want to destroy this because I want to be able to reverse anything that I do in the future. So what I'm actually going to do is I'm going to remove this heatsink from the PCB. I'm going to desolder those 2 wires, unscrew the 2 screws for the MOSFETs, and then remove that. And then I'm going to try and make an alternative heatsink to fit into that location. So depth wise, we have a lot of depth, but it will need to be narrower. It will need to have a step in it or be narrow at some point along here, so it will fit inside the vent that I just showed you earlier. So I'm going to go ahead and remove this heatsink and I will be back. Okay, heatsink removed. So there are 2 chunky thermal pads on there with insulators, so these obviously need to be isolated from each other and from the heatsink, so I'll have to bear that in mind. So the next thing I'm going to do is to find something that I can replicate the whole positions of these 2 onto, and then try and mount a couple of pins so I can remount something to the PCB that's nice and firm and solid. Okay, so this is what I've come up with. This is the original heatsink, and basically what I've done is I've taken an old heatsink that I had, I've cut it down. It's not exactly the same width, but it's pretty close. I've tried to make a couple of pins that are the same distance apart, which I think I've done pretty well. The pins themselves, not the best material. I really did struggle to find something to use for pins. I might have problems soldering this, but we'll see. So then I've relieved this edge so it will fit over the vent internally, and then what I've done is I've got one of these, this is an SSD heatsink and little fan, so I've drilled a couple of holes in that, and I intend to mount that onto there like that, and then I can connect this fan up so we can get some extra cooling. So I'm going to go ahead and put all this together, and then when I'm done I'll come back and we'll give it a test to see how it goes. Right, okay, so I've mounted the new heatsink, soldered the pins in place, and I've also mounted it's an SSD cooler with a little fan onto that heatsink. It's all very solid and rigid. I'm quite happy with that. I did put some heatsink compound between the 2 heatsinks. I also put a very small amount of heatsink compound on the 2 MOSFETs. I'm going to leave these thermal pads in as they are for the now, but I have got, if I think that these aren't performing very well, some old-fashioned mylar insulators which I can pop in there if I need to. So as it stands at the moment, I'm going to pop this back together, put the screen back on, and then we'll see how it performs. To start with, I'll do it without the fan, and then if necessary I'll connect the fan and see how that performs. Okay, so the first thing to do is to put the ribbon cable through the slot and then line up the terminals and the encoder, etc, etc. There we go. Okay, now I can put the screws back in. One, two, three, 4, 5, 6, 7, 8, 9. Okay, let's pop the ribbon cable back in. That. I'll just put a bit of tape on that for now so it doesn't get in the way. Right, there's the unit. There it is. So first things first, let's reconnect the terminals. Put a decent amount of torque on those. Good. Now hopefully it's going to fit. I haven't actually tried it. I think it will. Oh well, actually before I put that back in, so while I'm here, these fuse holders, so this has got a 15 amp fuse in and the other one I think it's a 10 maybe. I'm going to show you these guys on the internet because I believe that there may be an issue here as well. So anyway, so just bear in mind that this is a 15 amp fuse. The actual fuse holder itself, just as a rough idea, is about 10 millimeters across, just so we know roughly how big it is. Right, okay, let's pop that back in there. That fits nicely. So I'll leave the fan disconnected for now. I don't really want to connect it unless I have to, because that's just going to make more noise. Right, I'll just do that loosely for now. Okay. Right, I'm going to put the knob back on, I'm going to zoom back out and then set up for a test. I have in fact tested the unit without the little internal fan that I added connected, and although the running time was much longer before it overheated, it still did overheat. So now I have connected the small fan on the SSD heatsink up, and I've connected that in parallel with the cooling fan inside the unit. I did that just by making an adapter plug basically, so I didn't actually cut any cables or remove any plugs. I made an adapter cable which was connected to the original plug on the PCB for the fan, and then I just split that into basically two sockets so I could connect each fan individually. So what I'm going to do now is test this for the first time since doing that. So let's connect the power leads back up. Oopsie. Let's set my load for, okay, so I've got my load set for 8 amps. Turn the unit on. Okay, so we need to have a set voltage of 18 volts. Oops. And an output current of 8 volts. Set that for maximum. Okay, so we can see that the current temperature is 23 degrees. And yeah, so turn my load on, and we'll turn the output on. So it's at 45 seconds on the clock, and we're pulling 144 watts, and we'll just leave it and see how long it will run for. So the fan hasn't kicked in yet, so the temperature is increasing quite rapidly. It should kick in at 33 degrees, which it has just kicked in. See the light come on, you can probably hear that. I apologise for the noise. So at 1 minute it's gone up to 37 degrees. 2 minutes 41 degrees. 3 minutes 44 degrees. 4 minutes 46 degrees. So at 5 minutes we've got 48 degrees. It's already massively better. So I'm actually going to go and make a cup of tea, leave this thing running, and I shall return and we'll see what happens. Okay, so I've made a cup of tea. We're up to just over 11 minutes and it's at 52 degrees. 12 minutes, still at 52 degrees. 13 minutes, still at 52 degrees. So at 14 minutes it's gone up just up to 53 degrees. 15 minutes, still at 53 degrees. I've just adjusted the screen to get rid of a bit of the glare. I can now see myself drinking my cup of tea. So at 16 minutes we're still at 53 degrees. I think it's quite obvious now that this thing will probably run indefinitely at this load. So I'm going to terminate the test in a minute, and I'm pretty sure that this is what, personally I'm happy with it, so I think it's good to go. Yeah, 17 minutes, still at 53 degrees, so I'm going to call this a success. So I'm just going to turn the output off now. We'll see how quickly it cools down. I'll do that on the 18-minute timer. Okay, output off, 54 degrees. So after 30 seconds it's come down to 47. After a minute it's down to 42. The fan on my electronic load has just shut down as well, so you might have noticed a small decrease in fan noise. So after a minute and a half it's down to 39 degrees. Seven minutes, we're still at 30 degrees. And fan shut down at 7 minutes and 4 seconds. So it would appear as if I have resolved the overheating issue with this power supply. It's certainly way better, and for me it fulfills the requirements that I need from this power supply. There is one other alternative, or one other option that I may try in the future, and that is to actually install a much deeper cooling fan in the back of the unit. It's probably 20 millimeters deep, but you can get much deeper server fans at that size, so that would be a consideration. Either put a server fan in here which is, you know, much deeper, or you could actually put double up and put two fans back to back. So that is an option. Getting the fan actually closer to the heatsink would be a good idea, because the fan itself is a long way away from the heatsink. Even now with my extended heatsink, a massive gap between the fan and the heatsink itself, and the cooling vents don't really allow for correct circulation or flow of air over the heatsink. It's not a great design in my opinion. Anyway, having said all that, it seems to be relatively successful. So if you enjoyed this video, please give the video a thumbs up. If you enjoy this kind of content, please consider subscribing to the channel, check out my other videos and all that kind of stuff. So thanks for watching, and I'll see you in the next one.